Okay, hello everybody, and we continue. So, section 9.1. Let it be more integrable functions. More. Maybe not more. Classes, just. How to call this section? Riemann integrable functions. Integrable functions. Functions. More examples. Like that. Let it be like that. Sure. Okay. So, I'll start with a theorem about integrability of composition. Composition. So, suppose f is, let's start with g. G is integrable on AB let's say m less or equal than g of x less or equal capital M for all x in AB, and f is continuous on M capital M, little m capital M. Then the composition f of g, which is f of g of x, is integrable on AB. So please be careful. We have continuous function of integrable. That is important, in fact. Proof. So let's start with continuity. So f is continuous on our interval m little m capital. Hence, f by counter theorem. Counter theorem, f is uniformly continuous. On AB, MM, little m capital M. What it means? It means for arbitrary epsilon greater than 0, there exists delta greater than 0, such that for all, okay, let it be y and w in m, little m, capital M, such that y minus w less than delta for all such y and w, modulo f of y minus f of w less than, okay, let it be epsilon for a while. Maybe we should divide by something. We'll see later. I'll add maybe here some extra multiplier. Okay. Now let us think about function g. From g we know only about integrability. So g is integrable, and now I want to use Darboux integrability. Hence, there exists a partition P of the interval AB, partition, that is partition, such that difference between upper and lower Darboux sums is less than arbitrary given number, and this arbitrary given number will choose in a rather strange way, namely, let it be less than delta squared. You see, we had arbitrary epsilon greater than 0, right? We choose delta according to uniform continuity of the function f. So now we have delta. Delta is positive. And according to integrability criterion by Darboux, necessary and sufficient condition, there exists a partition of our interval AB, such that difference between upper and lower sums, Darboux sums for the function g, is as small as we want, and we want it to be less than delta squared. Okay, now we are interested in, let me introduce the notation f by definition is f of g of x. This composition is denoted by h of x, and we are interested in studying the difference between upper and lower Darboux sums for that function. And here some values will appear. Let me recall, that is sum I from 1 up to n. Let p is just a x naught, x1, so on, xn equals to b. So this n appears here, and I'll indicate supremums and infimums by capital Mi of the function which appears. So what is capital Mi of a function h, let's say? That is supremum over interval xi minus 1 xi of the function h of x. And analogously, little mi of h is infimum h of x for the interval xi minus 1 xi. Now, remember that when our function is given, and instead of h I can take here arbitrary function f, g, so it doesn't matter, right? Not f, of course, g. I can take here g as well, right? So instead of h I can take here g as well. Now, look, what is the idea? The idea is the following. So, we split our sum into two sums. So, we introduce two sets of indices. Capital A and capital B. And how we will introduce them? By definition, an index I belongs to the set A by definition. So, when we consider I as an index from our set capital A, if the difference between mi of j and little mi of j is less than delta. So that is the definition of the set of indices. So look how it happens. So we have indices. I runs from 1 up to n, right? 1, 2, and so on. We look at every I and look at this difference, right? If it is less than delta, then we consider this index I as an element of capital A. If not, then it will be in capital B. So B is the set 1 up to n without our A, by definition, or other indices. Now, what happens for I in A, capital A, with our difference? Delta xi. So, we are interested in understanding what is the difference between supremum, so what is, roughly speaking, maximal value of this function h, and what is h? H is, recall, f of g of x, right? So look, what happens here? If we know about this, what it means? It means that for arbitrary two, let's say x and t belongs to xi minus 1 xi, and I is in our capital A, then the difference between g of x and g of t in modulus is less than delta. This follows from that one. Look, because if we know that the difference between supremum and infimum is less than delta, right? Then difference between arbitrary values of the function is also less than delta. G of x minus g of t less than delta, right? But then, look, what happens? So, once we take arbitrary values x and t from our interval xi minus 1 xi, values of g of x and g of t has satisfied this inequality, right? Then it means by our choice of delta, we choose it according to uniform continuity of f. So f of g of x minus f of g of t is less than epsilon. This was by the choice of delta, so let it be inequality 1, this relation about uniform continuity, so that is by 1, by 1. Now, what it means? Look, I took arbitrary values x and t from our interval xi minus 1 xi. Then difference between values f of g of x and f of g of t is less than epsilon. So it means, by the standard consideration like I did during last lecture, that difference between mi, that is precisely h of x, and that is precisely h of t. So mi of h minus little mi of h is less than epsilon. Okay, so to make it small, I would prefer to change slightly 1, let it be epsilon over 2 times b minus a. Then here I have epsilon over 2 times b minus a, epsilon over 2 b minus a. Then it will be better. Why? Because now I can estimate the sum for indices I in capital A, mi of h minus little mi of h times delta xi. So every term in brackets less than epsilon over 2 times b minus a times sum I in capital A delta xi, and that is the sum of intervals is definitely less or equal to the length of the interval AB, so epsilon over 2 we obtain, epsilon over 2. So for the first sum we have an estimate. Now what to do with the second sum? So here we'll proceed as follows. Let us estimate sum for I in B firstly of only of delta xi, and put here also delta. By our choice of capital A, so I can write the following: mi of g minus small mi of g times delta xi. Why? Because of, look, here it is written, index I is taken from the set B, and the set B is a complement to the set A, right? So it means this inequality is not true here, right? So opposite inequality is valid. And what is opposite inequality? Delta less or equal Z1. That is precisely what is written here. Delta is less or equal Z1. Right? That is true just for indices from the set B, capital B. Now look, we have a sum. Every term is non-negative. If I'll add all other terms which are not included, then of course it will be larger, right? So I add some other terms. Less or equal sum I from 1 up to n mi of j minus little mi of j delta xi. I added all those non-negative terms which correspond to indices in capital A. But that is precisely difference between upper and lower Darboux sums for the function g. Maybe somebody could you close window, please? So that is precisely equal, right? Now, remember how we chose our difference. This is less than delta squared, right? Less than delta squared. So, what follows? It follows that the sum for I in capital B of delta xi is less than delta. Okay, now look, the function f is continuous, right? Hence, I'll choose one more thing. F is continuous. F is continuous. Hence, f is bounded. Is bounded. Modulo f of y is less or equal capital T for all y in MM by Weierstrass theorem. Every continuous function is bounded. Now, look. When I I choose here delta, right? When I choose here delta, the only condition was so for all yw which are less than delta, something should be satisfied, right? So if I choose some delta, then of course everything that was written here is valid for smaller delta, right? As well. So I can choose here delta smaller than what chosen before. So let me choose it from the beginning. Also delta less than 0 and delta less than epsilon. Extra supposition. Just from the beginning, it should be done, of course. So delta should be less than epsilon from the beginning. Then look, what remain. So sum for I in A is estimated, let it be 2. Now I'll estimate the sum for I in capital B. Well, the sum in I in capital B, mi of h minus little mi of h times delta xi. Less or equal. Okay, what are those values? Look, supremum and infimum of h of x. H is f at a point, right? So, maximal between those values is less or equal than 2 times c. So I can estimate it 2 times c times the sum I in B delta xi. That is, as we saw less than delta, so 2c delta, less than 2c epsilon. Oops. So from the beginning I should choose here epsilon over 4c, doesn't matter. So together with 2 it gives the estimate u of ph minus L of ph is less than epsilon over 2 plus 2c epsilon. Okay, epsilon was arbitrary, it means this is arbitrarily small number, right? So it means that function h is integrable. On AB by necessary and sufficient condition because of arbitrary chosen epsilon positive. So theorem is proved. Theorem is proved. Okay, let us apply that theorem to obtain some more continuous functions. So, corollary. Corollary 1. If f, g are integrable on AB, then their product f times g is integrable on AB. Proof. Firstly, we apply our theorem, apply theorem 1 for f of y equals to y squared, and okay, g is g, g is g. Of course, y squared is continuous function everywhere, right? And g is integrable, hence it is bounded, so in particular it is f is continuous on the interval which contains all values of our function g. So then g squared is integrable. All right? Analogously, so we know that square of an integrable function is integrable. Now it means that also f squared is integrable, right? F is integrable, hence square is integrable. And f plus g squared are integrable. Because we know the sum of two integrable functions is integrable, right? So we take square, again integrable. Now, f of x times g of x equals 2 can be represented as follows. there was a question why we need to know why this sum is less than delta. It is used here, right? So it was necessary for that. Okay? So f of x times g of x. Return to this. With help of those squares. That is 1/2 of f plus g squared minus f squared minus g squared, right? Of course, of x. Of x, of x, of x, of x. Right? So every square is integrable, difference is integrable, and integrable times a constant is integrable. So we obtain what we wanted. And let me emphasize that there is no rule to integrate the product. How to integrate, right? That is quite different from derivative. There is a rule how to find derivative of a product, right? But no rule to find integral of the product. Although, you see, for sure, if two functions are integrable, then their product is integrable. The integral exists, but we have no way to find it with the help of integrals of each of f and g. No way. Okay, one more corollary, second corollary. I hope no answer. Corollary 2. If f is integrable on AB, then modulo f is integrable on AB, and integral f of x dx in modulus less or equal modulo of integral of modulus, sorry. So we can put modulus inside the integral. Okay. We can put modulus inside the integral. That is estimate for integrals. Estimate for integrals. In particular, if modulo f of x less or equal than c for all x and b, then modulo of integral can be estimated by c times b minus a. That is rough estimate for an integral. So proof. Modulo y is a continuous function. Right? It's the same, okay. Is a continuous function. Hence, by, again, theorem 1, modulo f of x is integrable. So continuous function of an integrable is integrable. And then look, so both integrals are well defined, and now look, we know integral is a limit of integral sums when norm of partitions tends to 0. Let me write integral sum explicitly. Right? Then look what we observe. Modulo of the sum of arbitrary integral sum can be estimated like that. The sum of modulo times delta xi. So we know this tends to the integral f of x dx, and we take modulus outside. This tends to integral of modulo f of x dx. Hence, inequality is preserved by a limit process. And that's it. Corollary is proved. Okay. Let's have a break. Okay, let's continue. And let me give an example, a counterexample to a converse assertion. So, look, if f is integrable, then modulo f is integrable. Converse assertion is not true. If modulo f is integrable, it doesn't mean that the function itself is integrable. Why? Because look, example 1. Let f of x equals to 1/2 if x is rational, minus 1/2 if x is irrational. Then modulo f is what? Is 1/2 for all x in R, right? And it means modulo f is integrable over arbitrary is integrable on arbitrary interval AB. But what's about f? If you add f of x plus 1/2, then that is Dirichlet function. And we know this function is not integrable, right? Hence, f of x is also not integrable. So, you see, modulo is integrable, but the function itself not. Okay. Let's continue. Next theorem, 2. Theorem 2. If f is bounded on AB and is integrable on a b tilde for arbitrary for all, let me say, for all b tilde strictly less than b, and of course greater than a, then f is integrable on a b. So you see, if the function is integrable on arbitrary interval, so you see a, b, right? Shift little bit, doesn't matter how small is shifting, right? And if you know that the function is integrable on a smaller closed interval, right? And function is bounded, that's important. Then the function is Riemann integrable over the whole interval AB. Okay, proof. Take arbitrary epsilon greater than 0. Then let us choose there exists natural n, let's say, such that 1 over n is less than, let's say, epsilon over 2m, where f of x less or equal than m for all x in AB. We know the function f is bounded, so there is such a constant, and I choose one of them here. Okay, then look, put b tilde equals to b minus 1 over m. Then consider f is integrable on a b tilde, hence there exists a partition p tilde, partition of a b tilde, such that difference between upper and lower sums for that partition p tilde is less than, let's say, epsilon over 2. Now consider partition P, which is P tilde, together with the last point B. So what happens? Look, we had our interval AB, right? So we shift a little bit. That is B tilde. Here difference is 1 over n, right? Then here we have partition P tilde. Here P tilde, this set of points. And we add just one point, the last one, right? Then this is a partition of AB, right? A partition of AB. Now let us write the difference between upper and lower sums according to that partition. Then look, what is it? That is precisely upper and lower sums for P tilde plus just one term for supremum f of x in B tilde B minus infimum f of x for x in B tilde B times B minus B tilde. So both upper and lower Darboux sums for the partition P, by the definition, they differ from upper and lower sums for partition P tilde by one term, one extra term, which corresponds to the last interval, right? So U of P tilde F, we add terms which correspond to all those intervals, right? And one extra term is here, right? Now look, less than. The first difference, less than epsilon over 2. We choose P tilde from integrability of the function over a B tilde, right? For the second, look, difference between supremum and infimum less or equal than 2m, right? Difference between values of our function is less or equal than 2 times estimate for the model. And B minus B tilde is what? 1 over n, which is less than epsilon over 2m, right? So 2m. I made slightly worse. I wanted to obtain epsilon, but sorry. It's not so nice, but it is not important, of course, right? So you see, we took arbitrary epsilon greater than 0. We found a partition of interval AB such that the difference between upper and lower sums is less than arbitrary small number, right? Hence, the function f is integrable over interval AB as we wanted. Corollary, when it works. Corollary. If f contains only finitely many discontinuity points, on AB and is bounded, and f is bounded on AB, then f is integrable on AB. So how we proceed? Look. We have interval AB, right? AB. We have finitely many discontinuity points. Let it be D1 discontinuity point, D2, dk. Some of them may be at also, let's say, dk plus 1, maybe, right? Doesn't matter. Then what we do? Look, I'll separate it into several intervals such that, look, for example, consider a d1. Look, what happens for our function on the interval a d1? First of all, it is bounded, right? Because we supposed it's bounded on the whole AB. And also, it is continuous here everywhere except the point D1, right? In particular, it is continuous on every interval A, let's say D tilde, where D tilde less than D1, and of course greater than A, right? Because it is continuous here. And if it is continuous, then it is integrable. So look, continuous, hence integrable, and is bounded. So by theorem, f is f continuous, hence f is integrable, theorem 2, right? Integrable on a d1. And analogously, we consider every interval like here, right? Of course, if the discontinuity point is at the left end of an interval, it doesn't matter, right? It is not important. So, we obtain the function is integrable over every of those intervals, and by additivity property, it implies the function is integrable over whole interval. That's it. With the help of that corollary, I can now give you an example which shows that the conditions of theorem 1 are very essential. So, one more example. Example 2 for this section. Let g of x be the Riemann function. This is example 2 of section. It was section 8.2, I think. Point 1, no, classes of integrable functions. 1? Yeah. Riemann function, right? You remember it was 1 over m if x is rational m over n. G of x is 1 over m if x is m over n. Shortly. Right? Okay. F of x equals to 1. Let it be y. If y equals to 1, if y not equals to 0, and 0 if y equals to 0. So, look at the function f. It is continuous everywhere except for one point, right? Continuous everywhere except the point 0, right? So f is integrable by corollary over each interval, right? F is integrable on 0, 1, let's say, by corollary. G is integrable, we know from example 2, right? What is about f of G? What is it? Look, if x is irrational, then what happens? X is irrational, g of x is not 0, right? Then, if it is not 0, f equals to 1. So this is 1 if x is irrational, right? And if is irrational, then g is 0, right? G is 0, hence f is also 0. So it is 0 if x is not rational. And that is precisely Dirichlet function, right? Which is not integrable. So you see, composition of two integrable functions gives us non-integrable function. So you see, it's quite different if you compare, for example, with derivative. You remember, for composition of derivatives, just there is chain rule how to find derivative. But for composition of integrable function, even you cannot guarantee integrability of the composition. Only if you make extra supposition, f is continuous. Everywhere, you see, just continuity. You have only one discontinuity point, only one. But it's enough to destroy integrability of the composition, right? Okay. So now we have a rather huge extension of integrable functions. You see, composition continuous of integrable, so squares, for example, products also of two integrable functions are integrable. Also, you see, finitely many points is okay, and so many functions are integrable. In fact, up to now we have only one example of non-integrable function, right? No more yet. But I would say, in some sense, there are essentially more non-integrable functions than integrable. That is unexpected, but I'll not go into details. So, now, next section is related to differentiation and integration. So 9.2, section 9.2, integrals with variable upper limit. In fact, practically we had something similar in the last theorem today. We had function which was integrable over arbitrary interval, and right end of interval was arbitrary, so we could consider it as a variable. So what is it? That is, by definition, f of t dt, right? But to make this definition more convenient, let us give extra agreement. So f of a by definition is 0. Of course, we cannot integrate over one point. Makes no sense. But for the sake of simplicity, we accept this value. And also, if b less than a, then integral from a to b f of x dx will consider also let it exist, but by definition like this. So if we have wrong order of limits of integration, right, then no problem. Just put minus and consider limits of integration in the correct order. So no problem. Okay, these are extra suppositions. So now we have a function. So if f is integrable on AB, then the integral with variable upper limit capital F of x equals to integral from a to x f of t dt is well defined on the whole interval AB. Why? Because here we combine additivity property. If f is integrable over an interval, then it is integrable on a part of this interval. And also, no problem with the point A itself. By definition, we add this value, f of A is 0. So the function is defined. Now, what are its properties? So theorem 1, if f is integrable on AB, then capital F is continuous on AB. Moreover, if f is additionally, let me recall. So still we have the same supposition, f is integrable over the whole interval AB. Additionally is continuous at x naught. Okay, let it be in interval AB. Then capital F is differentiable at x naught, and f prime, capital F prime equals to little f at x naught. Proof. So you see that, roughly speaking, integral gives more properties for the function. So if f is only integrable, then integral with variable limit is continuous. If we have extra supposition about continuity at a point, then the function is differentiable at this point. So proof. let's start with the first part. So take consider x naught in AB, let's say, right? And x naught plus t is also, let it be in closed interval, no problem. Both x naught and x naught plus t are in that interval. Then capital F of x naught plus t minus f at x naught by additivity property and our agreement. So we have f of, okay, let it be s ds minus from a to x naught f of s ds equals to integral from x naught to x naught plus t f of s ds. F is bounded because f is integrable, hence it is bounded. F is bounded on AB. So f of x less or equal than capital M for all x in AB. So now it follows that we can estimate f of x naught plus t minus f at x naught. We can estimate as, that is, model of integral that is less or equal than capital M times, okay, I will write model of integral ds. Here you should be a little bit careful because t might be negative, and if t is negative, then you firstly should take in opposite direction, then apply the estimate and then go back. And that is precisely m modulo t. So what it means? It means that for arbitrary epsilon greater than 0, there exists delta greater than 0, and in fact this delta we can take just epsilon over m, which is greater than 0, such that for all t with modulo t less than delta, we have modulo f x naught plus t minus f at x naught is less than, you see, m capital M modulo t, and modulo t less than delta, so less than epsilon. It means precisely continuity at x naught. Why I took here x naught in the interval? Because for the point A we should consider continuity from the right hand side, and the point B continuity from the left hand side. But of course no difference, right, in the proof. So first part is proved. Now for the second part. For the second part, look what we have. F, we should prove that f is differentiable, and we should prove this equality simultaneously. What it means? It means that we should consider the following limit. I want to prove this tends to 0 as t tends to 0. Why? Because, look, this tends to derivative, right? So I want to prove this tends to 0 as t tends to 0. If I'll prove it, then we are done. Okay. We know the expression, so I'll write it here. 1 over t integral x naught plus t f of s ds. And now here, that is a constant, right? So I'll represent it also in the same way. X naught ds. Because you see what is written here. That is a constant, right? And integral is equal to precisely t, so that is f of x naught. That is strange way to write down f of x naught, like that. Then what is it? That is 1 over t integral from x naught to x naught plus t f of s minus f of x naught ds. Now look, we know f is continuous, right, at x naught. It means that, what can we observe? Look, f is continuous at x naught, hence, by Cauchy definition of continuity, for arbitrary epsilon, there exists delta positive such that for all t with modulo t less than delta, we have inequality f at x naught plus t minus f at x naught less than epsilon. Now look, I'll estimate the difference so according to our writings, that is 1 over t integral from x naught up to x naught plus t f of s minus f of x naught ds. Now we have an estimate. So look, 1 over modulo t, modulo of the function under the integral. Look, if modulo t less than delta, right, then here difference between s and x naught is also less than delta, right? Because s is on that interval. So the function on the integral is less than epsilon. So I can put epsilon outside and have then integral ds, which is precisely modulo t, so that is epsilon. And that means, because of that sequence, so we have limit as t tends to 0, f x naught plus t minus f x naught over t equals to f at x naught. It means the function capital F is differentiable and its derivative coincides with the function little f. So it means we have a nice way to find a primitive, right? So if the function is continuous on the whole interval AB, then you can find a primitive. How? Corollary. If f is continuous on AB, then capital F of x, which is just integral with varying upper limit, is a primitive for little f on AB. So we have a nice way to find primitives. And in fact, it works in opposite direction, of course, usually, because it is essentially easier to find a primitive by indefinite integration than to compute the Riemann integral by definition. So it gives vice versa a way to compute integrals with the help of primitives. Okay, but we'll do it during next lecture.